What's up guys, Asher Siegel Codes here, back with another video, and today we're going to be going over a project from the course COS 126, which is Princeton's Intro to Computer Science course called Plucking a Guitar String. And so basically we are going to be using our keys to make notes into the computer, and we will get output of sound. So let's start with the intro. Write a program to simulate plucking a guitar string using Strong algorithm. This algorithm played a seminal role in the emergence of physically modeled sound synthesis, where a physical description of a musical instrument is used to synthesize sound electronically. Digital audio. Before reading this assignment, review the material in the textbook. We don't need to read about that because we don't have the textbook. Simulate the plucking of a guitar string. So this is about the project that we're going to do. When a guitar is being plucked, the string vibrates and creates a sound. The length of the string determines its fundamental frequency of vibration. We model a guitar string by sampling its displacement, a real number between -1/2 and +1/2 at n equally spaced points in time, where n equals the sampling rate of 44,100 divided by the fundamental frequency, where the quotient is rounded to the nearest integer. So you can see we have some important numbers, -1/2 and 1/2. So our ring buffers, which I'll talk about in a minute, will not be exceeding or going under these restrictions. And 44,100, which is a number we don't really need to know about, but it's just from the equation of the Strong algorithm. So let's get into this. Plucking the string. The exactification of the string can contain energy at any frequency. We simulate the exactification by filling the buffer with white noise. Set each of the n sample displacements to a random real number between -1/2 and 1/2. Here we can see that none of the displacements go over 1/2 or under -1/2. The resulting vibration. After the string is plucked, the string vibrates. The pluck causes a displacement which spreads a wave-like over time. The Strong algorithm simulates the vibration, maintaining a ring buffer of the n samples. The algorithm repeatedly deletes the first sample of the buffer from the buffer and adds to the end of the buffer average of the first two samples, scaled by an energy decay factor of 0.096. So what you're doing is you have your ring buffer here, and you have the first two. You remove the first frequency, and you're just going to remove it completely, as you can see here. And you're going to add these two, average them. So here would get 0.2 and 0.4 would be 0.6, and 0.6 times 1/2 is 0.3, and then that times 0.996 is 0.2988, and then it would play. So now let's review why this works real quick. The two primary components that make up the Strong algorithm work are the ring buffer feedback mechanism and the averaging operation. The ring buffer feedback mechanism. The ring buffer models the medium in which the energy travels back and forth. The length of the ring buffer determines the fundamental frequency of the resulting sound. Sonically, the feedback mechanism reinforces the fundamental frequency and its harmonics. The energy decay factor models the slight dissipation in energy as the wave makes a round trip through the string. The averaging operation. The averaging operation serves as a gentle low-pass filter, which removes the higher frequencies, allowing the lower frequencies to pass, hence the name. Because it is in the path of the feedback, this has the effect to gradually attenuating the higher harmonics while keeping the lower ones, which corresponds closely with how actually plucked strings sound. So we are going to have a ring buffer class, and as you can see here, they kind of labeled a diagram for us. So we're going to have the constructor, which has a parameter of capacity, size of the ring buffer, a boolean of is empty if it's full. We're going to enqueue, dequeue, and peak. So let's get started right here. And it says right here, since the ring buffer has a known maximum capacity, you can implement a ring buffer using a double array of that length. For efficiency, use cyclic wraparound. Maintain one integer instance variable first that stores the index of the least recently inserted item. Maintain a second integer instance variable that stores the index 1 beyond the most recently inserted item. To insert an item, put it at the index put in the index last and increment last. To remove an item, take it from index first and increment first. When either index equals capacity, make it wrap around by changing the index to 0. So we're going to need this in the beginning. And let's open a BlueJ file right here. And I'm going to click out of this so we can start from fresh. And we're going to look at the ring buffer. So here we go. So you can see we are tracking the size, the front and the rear, the capacity as well. And then it said to create an array, a double array of that length of the capacity, which was passed in, which we'll see in a second, through the ring buffer. So we have double array of ring buffer, and it is passed in with the capacity, and this dot capacity, so our capacity right here is equal to this capacity. We just clear the ring buffer. So here are some normal getters. Size just returns the size. Is empty if the size is equal to 0. If it's full, if the size equals the buffer dot length. And now the add. So it says add item X to the end, which is fairly simple, but we still have to keep in mind of cyclic wraparound. So if the size is less than the length, and if the rear is greater than the buffer dot length minus 1, then we're going to be setting the rear equal to 0 as the first element. And then after that, ring buffer at the rear is equal to the value, and then we increment the size and we increment the rear like it said here. Increment for last, an increment to last. If the rear is greater than the buffer dot length minus 1, then we're just going to set the rear to 0, because then it would be going past. Clear, we just create a new array. The size is equal to 0. Front and rear are both equal to 0. Peak, if it's empty, we just print empty, and then if it's not, then we return the ring buffer at the front, which would be like this 5. It's just the front of the array, since we're using a floating index array from an array. And remove, we have our num. We're going to store that at the beginning before we remove everything, so we're able to return it. So we have double num equals ring buffer at front, which is the one that we're removing. We're going to increment the front, and if the front is greater than the ring buffer dot length, so that if it's the last one in the array, we're going to set it equal to 0 for the cyclic wraparound. We're going to decrement the size by 1, and if the size is now greater than or equal to 0, we're going to clear the entire array. And then we're going to return this num, which was at the front of the array. And that's it for the ring buffer class. That came with a tester, as you can see right here, which I did not make, but it came in the project, and we can test it here. Size after wraparound is 150.5050.0, which we're supposed to get, I'm pretty sure. Maybe. Oh, you are supposed to get that, but it's on the assignment. It's on a different page. I will post a picture of it, or actually, I'll just go to it right now. We can see here that maybe it's in Guitar Simulator. Here we go. Now we download the directions, and now all we have to do is download directions. Here we go. Sorry for this quick delay. Size after wraparound is 150.50.0. So we are doing this correctly right now. Sorry for that quick delay, and let's get right back into this. Alright, so now we're going to go to the guitar string class. So here, let's open guitar string, and we have a much more complex class as it looks to be, but actually it's not. So we have two constructors here. We have a frequency and an array, and they both create instances of guitar string. We have a pluck, a tick, and then a sample, which returns the current sample, which we'll get to in a second, and the time, which is just the number of times that the guitar has been ticked. So for the constructors, there are two ways to create a guitar string object. The first way is the first constructor creates a ring buffer of the desired capacity and sampling rate 44,000, which was declared at the top, and we see again here, divided by the frequency rounded to the nearest integer. So what we're going to have to do, if you guessed it, is cast an integer. And so we have our capacity, we casted an integer, and then we rounded the sampling rate divided by the frequency, which it says to do here, sampling rate divided by frequency, which was passed in as a parameter. And now we create this integer of capacity and create a new ring buffer of capacity. And then we cycle through the ring buffer and we just add a flat 0 to every index because we don't want anything to be played or any frequencies. So the next one, the second constructor creates a ring buffer of capacity equal to the size of the array and initializes the contents of the buffer to the values of the array. On this assignment, its main purpose is for debugging and grading, which we don't really need to worry about. So it does basically the exact same thing as the one above, but with this new array. And it just cycles through the ring buffer and adds whatever was at from the array, just copies it. Let's get to the pluck method. Replace the n elements in the buffer with the n random values between negative 0.5 and positive 0.5. So for here we have ring buffer dot remove. So it removes the item at wherever we are, and it sets, we have double num, and we can see that math.random minus 0.5 will give us a number from negative 0.5 to positive 0.5. And then we add the ring buffer. We have the math. I don't know why this should be actually same thing as num. You can just put num in there. So we add num to the ring buffer, and we'll just have a bunch of, let's say, negative 0.21, negative 0.4, positive 1.14 at all of these indices in the array. And now let's go to the tick. Apply the carpless strong update. Delete the samples at the front of the buffer to add the end of the buffer, the average of the first two samples multiplied by the energy decay factor, which was 0.996, I believe. Yeah, 0.996. So we're taking these two, averaging them, removing the first, and adding the product to the end. So as you can see right here, we have the first one which we remove, and the second one which we peak. So the first one was removed, and then we add to the end of the ring buffer the energy decay factor 0.994 times the average of these two, and then we increment the tick counter, which we are going to need for time. But let's look at sample. Return the current sample. So all that does is it just returns the top, which we can see, ring buffer dot peak. It's just going to return this one, for instance, if we're getting the sample. It's just going to return the peak. So if we remove this one, then it's going to peak this one. And if we don't remove that one, then it's just going to be the first one. And now time, it just returns the number of times that tick was called. So we call tick, tick goes up by 1. In tick counter, we just return tick. We just return the times tick counter has been called. Or tick has been called, I apologize for that. And now, let's go down to the interactive guitar player. Guitar Hero Lite.java is a sample client of guitarstring.java, sdt.draw, and sdt.audio that plays the guitar in real time using the keyboard to input notes. When the user types the lowercase letter A or C, the program plucks the corresponding string. The combined result of the several sound waves is the sum of the individual sound waves. We play the sum of all the string samples. So we're going to be using this sample, we're going to be using tick, and let's give a look at this code right here. So we have this 440, this was mentioned earlier, and what this 440 is what's actually mentioned later. I apologize. It's the ith character of the string to a frequency 440 times 2. So that character Q is 110 hertz and character I is 220 hertz. V is 440 hertz and space is 880 hertz. So what we're trying to do is we're finding the frequency in this 440 times 2 to the I minus 24 divided by 12. It's just a formula, so you don't need to worry about it too much. And we can see appear here math.pow to the 3.0 divided by 12, and we can see sdt.draw has next key types. We don't need to worry about this sdt.draw, but has next key type. So when I type a key, it's going to run char key equals the next key typed. So let's say if it's A, this key is going to be A. If key equals A, we pluck string A, and then if it's C, then we pluck string C, and then this sample is string A.sample plus string C.sample. So if string A was sampled, then it's going to run string A. If string C was sampled, then it's going to run also string C, and then the sample is going to be played in this audio player, and then we tick both of the strings from advancing the simulation. But here's the thing. It says write a program Guitar Hero that is similar to Guitar Hero Lite but supports a total of 37 notes on the chromatic scale from 110 Hz to 880 Hz. In general, make the ith character of the string keyboard equals, you can see QWERTYUIOP. So we have this top row, and we have 2, 4, 5, 7, 8, 9. And so we have some of the keys at the top, and then we have a bunch of other characters. So this keyboard arrangement imitates a piano keyboard. The white keys are on the QWERTY and ZXCV rows, and the black keys are on the 1, 2, 3, 4, 5, and ASDF rows of the keyboard. And we can see here we have this frequency, which I was just talking about, equation. So we're going to show the implementation of this real quick. So now instead, let's compare. Instead of theirs, we created our own notes, and we're just going to put all the frequencies of the different notes. So we're going to use this frequency of the equation from right here, and we're just going to have this frequency and create a new guitar string in the array of notes, so at all the indices, and we're just going to make it keyboard.length size. So it's just going to be this, and it's going to be every single note, and with that note is going to come its frequency, and we're just going to be putting its frequency in there. So we have the same thing right here. Char key equals sdt.next key typed, except since we want to have a bunch of keys, we're taking in a new key. We don't know which key it is. It's not only A or C. It could be Q, W, E, R, T, Y. It could be all these random keys. So, So what we're going to do now is we're going to get the index of it, and if I is greater than -1, so if a key was typed, then we're going to pluck it. So you can see here, and then double sample. We don't really need to worry about this, but this is what matters right here, this enhanced for loop. guitar string S through notes. So for guitar string S in this frequency of all of these frequencies of the notes, we have this double sample and we add it to S dot sample, so it samples all of the notes, and if it is played, if a note has a frequency corresponding to it, then we play it through the audio class. And then for guitar string S in notes, we tick it, so you can see it ticks A and C here, and we are going to be ticking all of the ones in notes. And that is all, and let's play it right here. Click on the file. And that is it. I really hope you guys enjoyed this run through, and I will be posting this on GitHub if you guys would like to check out the code or play yourself. And once again, thank you guys for watching and have a great day.